Hey YouTube, welcome back. Problem number 222, count complete tree nodes. So here, given the root of complete binary tree, we need to return the number of nodes in the tree. Okay, so in a complete binary tree, the number of nodes can be calculated more efficiently by first using the tree height, number two, avoiding unnecessary recursion if subtree is perfect balanced. Okay, we can solve this in three steps. Let me write them here for you, but let me just okay. We can write them here. We can write them here. Okay, so number one, we will define two helper functions. Like we will add like a two helper functions. We basically have one called a get left height, and the other one it will be named get right height. Each one of them returns the height from the leftmost path or the rightmost path. Number two, we will basically, if the left height equals the right height, we returns the height from the rightmost path, and that's it. Basically, sorry, the tree is perfect, and we return we square like right and get take one of them, or maybe like we square left. Basically, the total nodes will equals 2 in the power of h, which is h here is the height, and minus 1. If that wasn't the case, we will basically will recurse the left and the right, and we add 1 to them, and that's it. Like recurse. Okay, so how are we going to do that? First, let's start with the two helper functions. Let me put the code far left. So in the two helper functions, I will have first function, I will call it get left height, and it will take node as an argument, and I would say let height, which will equals 0, and we should return that height. And I'll create a while loop. Basically, while there is node, we will add height plus plus. We'll increase that by 1, and node will equals node dot left, and that's it. And actually, the right, it will be exactly the same. If we want to optimize this function, we can just make one function that will accept both. But yeah, I'm not feeling right doing it right now. Right, I guess node will be node dot right, I guess. Right, no, there is an h. So okay, we did create the two helper functions that we need. Right now we will work with the code. First, I guess there is a base case that we need to address. Like if we have no root, we need to return 0 because there is no height. If there is no root, there is no height. We return 0. Okay, so let's start here. Let left height will equals get left height here, and I will add the root to it, and I guess let right height will equals get right height here, and I put the root to it as well. Okay, I'll create an if statement. So if left height, let me copy it, because I guess if left height equals right height, that means we have a perfect binary tree. So what are we going to do? We return 1 in the power of left height minus 1. Okay, if you don't know what this means, if you don't know what this means, we need to address this because, yeah, I guess if you're interested in your interview and your interviewer sees something like that, I guess he or she will ask you about that. So, if you wanna break down this, what this do first, this lines will calculate the total number of nodes in a perfect binary tree of height left height. Okay, so again, a perfect binary tree. Oh, a perfect binary tree is a binary tree in which all levels are fully filled, including the last levels, and the number of nodes in a perfect binary tree of height h is is basically the number of nodes. It equals n to the power of h minus 1. How to do the power of h here in the keyboard, I don't know. So it will be n in the power of h minus 1. What this is looking like, this is a bitwise shift. So this is the same as we make like math dot pow to at left height. It is the same. So yeah, but we just doing it like as a bitwise shift. So yeah, it could work as both. Okay, in fact, I might use this because this is easier to be readable for you guys. I guess using bitwise is not is not fun for a lot of people. They don't like it because it doesn't make sense. So let's use meta.pow. I guess it will be good. But what should we do if the tree is not perfectly balanced? If that was the case, we will return 1 because we have the root. We add 1 and we add we call the count nodes because we recursively call the bigger function here count nodes, and I would count nodes, I will call it again on root.left, and we add here count nodes. No. On root.right. Okay, so again, let's try to understand this. 1 minute. So let's run first before doing anything. So we have problem here. Math.pow left height is not defined. Why? Oh, sorry. No. Yeah, it's works. So okay. If we wanna, okay, let's submit it and after that we will describe the code. Okay, everything works. Okay, so let's just try to submit to describe the code more in details after solving the problem. So again, you are given the root of a complete binary tree. You need to count the number of nodes in the tree faster than O of n time. This is the thing that we need to think about. So the key idea is to complete a complete binary tree has special structures. First, all level expect that possibly the last are fully filled. Number 2, all nodes in the last level are as far left as possible. Okay. So instead of visiting every node, which takes O of n, we can use a tree height and structure to count nodes faster using binary tree pointers. Binary tree properties, not pointers, sorry. So if we're looking to the code, first we have here if there is no root, we return 0. This is a base case. If the tree is empty, we return null. And since we're calling this function over and over, it's a recursive function. You need to start always by thinking with your base case, because if you have no base case, that means the function will run endlessly forever. Here we have the left and right height. This one, it's a pretty simple. It's the number of levels from root to leftmost leaf, to leftmost leaf, and again here in the right height is the numbers of levels from root to the rightmost leaf. Okay, so here if the left height equals right height, that means the tree is perfect. So if both left and right height are the same, this is a perfect binary tree. In a perfect binary tree, the height number, I will put it here for you. The height number will be the number of values. It will be it will be 2 in the power of h minus 1. We will calculate it instantly. No need to visit every node at all. If the tree is not perfect, what should we do? In this case, we will, if the tree isn't perfect, we will recursively count the nodes. We count 1 because which is the root. We add to it plus count of nodes on the left tree, and we add plus count node on the plus count of nodes in the right subtree. We have here two helper functions. Each one of them walks down. For example, the left height will walks down left children of the tree, counts how many levels deep the tree goes on the left side. And the right, I guess it is the same. It's not, I guess it's actually the same. So why this works? Because in a complete binary tree, if the left and the right height matches, it's perfect binary tree. So we do fast calculation. If not, we split into smaller subtree and count recursively. So yeah, that's it. The problem. And I hope you like the code and I hope you like the solution. And yeah, see you in the future.